Okay, so as I was kind of going around, hey guys, I'm lecturing now. Thank you. So as I was going around, looks like everybody who attempted, but by and large, most people who attempted the second question nailed it. I was a little worried about that, but it looks like by and large you can read, which is good. The first one, I haven't had the opportunity to look at. I think it went a lot better than I anticipated, just because in the past couple of years, it's been pretty. That's usually the rough quiz. So I will see about that. I hope I'm proven right that I'm expecting you guys to do really well on this quiz. Everything that we've been doing up to this point has been leading to building this processor. So I think at the beginning of the semester, I tried, freaking you out a little bit by showing you this diagram, or the one from the textbook, which is the full advanced digital system. This is the full computer architecture that we will be building to. So a very common question is being able to actually, if, let's say, Teresa was in the interview and we're all on her board, we say, provide her the copy of the, or we asked her to study the Patterson-Henderson textbook. All right, draw me up a full MIPS data path. All right, draw me a reduced MIPS data path that only performs R-type and I-type instructions. Show me how you would do things in a pipeline structure, right? So what we're going to be doing here is we're going to actually be building to it. We're going to be showing how to put these together, kind of learning the fundamentals of each part and how these all tie together. And what you'll probably figure out is as you're building these pieces together, what you did just now on the MIPS coding is actually going to make even more sense, because you'll actually say, oh, that's what the registers are. Oh, that's where it's going to the arithmetic logic unit. Oh, that's where it's going to the data memory. Oh, that's what the opcode actually physically is. That's what a shift amount actually is. So the whole goal is to actually, by learning this data path and then being able to not only just be able to reproduce it from memory, but actually do what's the question you'll see on the exam is a reduced version that you'll be asked to take certain parts out. If let's say I give you an R-type and a J-type instruction. Well, there are certain parts of the data path that are only needed by I-type instructions, so you can actually remove those. So you can demonstrate to me that you understand the functionality of the advanced digital system. So the first part, if you recall from what are my 5 stages of my MIPS data path? The first one's right there, instruction fetch. Yes. So what are the other ones? Decode, okay. Execution, someone else for my last 2? Right back to the 5th one. What's the 4th one? Data memory. Okay, very good. So good job. Someone read from their notes. All right, so but what is this actually? All right, so we talked about this byte addressing, which is, Emily, what is byte addressing?
Byte addressing.
Yes, we did. We talked about this yesterday in office hours. That's why I'm picking on you.
I know. I'm trying to remember the definition we talked about. I know this is 4.
Well, don't think about the definition. Think about intuitively what it means.
Well,
make your best attempt.
There's 32 bytes.
Correct.
Broken into 4 blocks of 8.
So you're right. Very good. That is exactly what byte addressing is. We have each memory address in MIPS is 32 bytes, or 1 word, and it's broken down into 4 blocks or 1 byte, which is why it's known as byte addressing. That's done in both the instruction memory and data memory. What we're going to see here is that the instruction memory and data memory are split up. And that split up is what's known as a Harvard architecture. Well, I don't have that as a definition. You're going to see that term come up a lot when we get into the cadence tools, particularly the 10 silica. They say, oh, this is a Harvard architecture. All that means is that the piece of memory where we have the instructions stored, and the piece of memory where we actually have our arrays and pointers are separate. And the reason why is we're trying to avoid something known as a structural hazard, which we'll cover a little later. But the general idea of the instruction fetch is we have the program counter, which contains the address we're pointing to, the instruction memory itself, which takes in a read address and an instruction. So the program counter So in the quiz you just did, we started at 256, right? So here's the difference between what you see. So what you wrote down, you did 256, 257, 258, and so on, right? So here's a good example of the difference between coding at the, and then how it's actually working at the architectural and organizational levels. So 256 is what your instruction is going to be. That's the actual physical value that it will start at. What's going to happen is 256 goes here. We get our 32 bits. But what's actually happening is we're getting byte 1, right? Byte 2, byte 3, byte 4. They're put together, and then they're put out on the instruction. So what's actually going on here is the number is actually going here, and 4 is being added. So this becomes 260. Well, okay, so let me get rid of this. So it was 256, 257, 258, right? And I told you that in order to calculate the address, you do 256, or you do, in this case, it was like 264 minus 258 minus 1 times 4, right? So what's actually happening here is this isn't 256. This is 256 times 4, right? And so this is 256 times 4. And this becomes 256 times 4 plus 4. Because what happens is this is 256 times 4, 256 times 4 plus 1, 256 times 4 plus 2, 264 times 3. And you put those 4 bytes together to make one word, and that gives us our instruction. So this becomes the next instruction, the next byte here, which is 256 times 4 plus 1. The reason we do this addition is so that way, in the event that we just came back and just got the next instruction, we'd immediately get that byte and then the next 3. Does that make sense? That is why we do the plus 1 there. So it's actually physically done in the advanced digital system. So when you see 256, 257, just really coming out great on the screen today, 256, 257, 258, what it's seeing is times 4, times 4, times 4. So let's say I wanted to branch to 259, right? From 256. Let's say 256 was a branch equivalent instruction. So what that means is we actually already, the value that's going to be going to our branch logic is this value here, that 256 times 4 plus 4, right? So what's going to happen is we're going to say, all right, 259 minus 256 minus 1, which is because of this adder that we're adding 4 every time. And then we multiply by 4 because of byte addressing. So we get out of instruction memory, instruction fetch, and now we're actually decoding the instruction. Okay, before I move on, does that make sense so far? Right. So it's instruction decode. What we're actually doing here is that the output of the instruction may be an R-type, I-type, or J-type instruction. As we've established, if you look in your MIP screen sheet, the 3 types of instructions are down here in the bottom right. So all of them are 32 bits, correct? So we have to come up with some physical way that we can differentiate it. And that's what this stage is going to do. So the first thing we're going to do is we're going to send the first 6 bits, the 6 most significant bits, 31 through 26, to our controller. And that controller is going to determine our control signals that will control everything through the rest of the data path. 25 through 21 is going to be RS in the case of R-type, N-type, and I-type instructions, right? And then J-type, we'll deal with that in a bit. I-type, it can either be RT, which is going to be a source register in RS, or RD, it's going to be a destination register and an I-type instruction, correct? So remember how we have to like, you just knew at that point that it either has to make some kind of decision, or we're going to be using some sort of decision logic. Now, what's the decision logic that I mentioned earlier in the semester that starts with an M? You have two inputs, you have some sort of select logic, and one output, and you have to pick one of them. Multiplexer. Really good. All right, you learned something this semester. I can prove it. The ABET people are coming next week, so. So then what's happened is we send the 16 bits from the I-type instruction down below the registers to indicate that we might be able to send that to the ALU later. So we have these are known as control signals, and there's 9 of them in MIPS. I'll expect you to be able to describe all 9 of these. But it's pretty straightforward when you really think about it. Register write, used to indicate if a register is being written to or not. 1 if yes, 0 if no. So it's formally defined here. It's used to indicate if a register is being written to or not. If 1, then a register is being written to. If 0, no register is being written to. On an exam, I wouldn't expect you to be word for word. The only one I ever really expect you to be essentially word for word is architecture organization. As long as the words that you're using actually convey that point, you're fine. So if you say register indicates something is going to be written to, 0 if yes, 1 if no, then you're going to lose a lot of points. Yes, Alex.
That's 1 if any register is being written.
Correct. Exactly right. If it, for example, it's an R-type instruction, right? So Emily, when you were in on my office hours yesterday, we talked about how an R-type instruction is you take 2 registers, perform some sort of operation, and then store the result in the 3rd register, correct? So for every R-type instruction, reg write is going to be 1. Because the register that's indicated in RD is being written to. So shift left logical. I've taken something out of one of the registers. I'm shifting it by 2, right? Shift left logical by 2, and then storing the result in another register, correct? So in this case, reg write is also 1. So this other one known is register destination. So remember I was just alluding to how we have to make a decision between whether or not the destination register is going to be RD, that 15 to 11 in I-type instructions, or 10 to 6 in R-type instructions. So register destination is used to determine if the RD or RT register is being directed to the right register. So these two control signals work in concert. It means 1, if register write is 1, I want something to be written to in the registers. If it's 1, then what I care about is, well, which one am I choosing? And we're going to see here in the drawing down here in a second that you're making a decision between 2016 and 15 to 11. Which value am I actually writing to? So this means that if it's 20 to 16, then I'm going to be doing RS and I'm going to do an RT, right? Which means it's an I-type instruction. If I'm going to be doing RD, which is 15 to 11, it's an R-type instruction. So this register destination, if I'm able to determine with the opcode if it's an R-type or I-type instruction, I will be able to automatically choose which one of those 5-bit instructions I want to use. So used to determine whether the RT or RD register is being directed to the right register, controls a must. If 0, it's an I-type instruction, and instruction 20 to 16, so that is 5 bits, is sent to the right register. So that means, if you remember from the memory addressing, remember I had the 5 to 32-bit decoder that determined which one we're doing. So each of these rows of registers, which are 2 dual-read single-write SRAM, what's happening is you get a write register value, which goes to the right, and also we have a value coming in saying, I specifically want this one. So let's say we had this one, right? So what's going to happen is it comes in, we get our 5 to 32, and we get 32 values coming out. The 16th one is going to be selected, so we have write register going in here, and it's like a bunch of AND gates. And since this is the one that has both AND gates, the value of 16 and reg write, then we can actually update the register with the value that's coming back. Otherwise, we don't. Does that make sense? If 1, then it's an R-type instruction. And the instruction 15 to 11 is sent to the write register. So in that case, we're getting the value from RD, from your R-type instruction, and that's being decoded. And then that value is being written to in the registers. So reg write is being sent to the registers. Register destination is being sent to a multiplexer outside of the registers. And so, as I've already mentioned, that 15 to 0 is decoded. One other control signal that you should bear in mind is the ALU op. So if you recall from the arithmetic section, right, we did a bunch of topical guide objectives regarding logic inputs from quote to the ALU as a 4-bit value, and then we had the ALU controller, where we had a 6-bit value coming in from the function and a 2-bit ALU opcode. In this case, the ALU op is determined from the opcode itself. It's sent to the controller, and then the ALU opcode is then sent to the ALU controller. And so the next topical guide objective down here is going to be the drawing, and I'm going to go over all of this again. But the formally defined ALU op is a 2-bit control signal sent to an ALU control with the funct from the instruction, so the function, which is used to determine the control signal input to the ALU. So if you recall that 4-bit input that drove the 16 to 1 multiplexer, right? That's how we're starting to determine that value. Does anybody have any questions so far? So this is the instruction decode stage. So here's what happens. We get the 32 bits from the instruction memory. And while I don't have it in this specific TGO, this goes up to a controller, which is 31 to 26. Now, I'm going to say this now, and I will say this again to you approximately 5 times before the exam. And this is actually very effective. Nobody ever forgets the controller when I say this. I always tell people on the data path problem that if you don't include the controller, like I've done there, then I will dock you 5 points on a 25-point question. So why do you think I would hit you so hard on that? Okay. So why is it really important? The name of the course is Advanced Digital Systems, right? So if you recall from the very first lecture, in order to make an advanced digital system work, you have to have a controller, which, if you remember, I was running around in the back and saying you all the back of the controllers and you all are the execution thing. If you don't include a controller, your data path is not in control and doesn't do anything. So if you don't include the controller, your data path doesn't work. Everything else is just, it doesn't work properly. If you don't have a controller, it doesn't work at all. Does that make sense? So usually I do that, and this is the 7th time I've been teaching this class. I don't think anybody's ever forgotten the controller. Yes?
In our TGO for this, should we include the controller?
You may. I mean, it's going to be in the next one as well. But, okay, so I included that for this reason. So you had instruction 25 to 21. You can just put, for brevity, you can just put 25 to 21 like so. You don't have to write out instruction every time because you're going to run out of paper. Or you can just do 20 to 16, 15 to 11, and 15 to 0 for brevity here. So here's what's going on. We have 32-bit output, which is 4 bytes because we're using byte addressing, goes to our control signal. 25 to 21 is RS. It always goes to the registers no matter what. 2016 This is RT, and 15 to 11 is RD. So if it's an R-type instruction, we're going to go to a second read register, and these values will come out here as 32-bit values, right? Now you can guess that we're going to have more multiplexers out here to clarify all of this. But for the time being, we just have 32-bit value. To determine which value we're going to be writing to, if it's an R-type instruction, let me do orange here. If it's an R-type instruction, it's RD, correct? So it's going to be 15 to 11. So we would be going through RD. Remember from the definition that the multiplexer is 1, and that the control signal here is this value that says register destination, right? Regdest, R-E-G-D-S-T. That means if it's 1, it's going to be an R-type instruction, so 15 is going to be the write register. And if we're actually writing to it, then register write is going to be equal to 1. If it's an I-type instruction when we're updating a register, we're going to use RT as the result, right? Because it's the multiplexer is going to be the value of 0, and then regwrite is going to be 1. So for those of you who did the number 2 correctly, your first instruction was you came up with some temporary register. I think it was S4 and then 5, right? Remember that? So what happened is T1 is the value that's coming here in 2016. S4 is 25 to 21, comes out through here. The value of 5 is the 16 least significant bits that comes out here and is sign extended to a 32-bit value. The other thing to note, if you remember from the R-type instruction, the 6 least significant bits are the function, right? So we get these last 16 bits, of which the last 5, this is 5 to 0, is your function. It's not sign extended, and it goes to your ALU control. The ALU control also has an ALU op here. So this is the ALU controller, which is going to send a value to the ALU here that we're going to discuss here in a moment. So does anybody have any questions about the instruction decode stage? All right, so everything we have here is now going to be moving to the execution stage. We have now taken these 5-bit register values. We now actually have our 32-bit register result, or that register addressing. So now we have the immediate addressing, right? So now we're starting to cover all of our different types of memory addressing from that previous section, right? So here, let's see. So what's happening is we have a potential R-type or I-type addition, right? So in your question that you did, you had an add I, or you had to add 5, right? But then the next instruction was add the second register. So what's going to happen is every single time, no matter what, you're going to get a value from 2016 to come out on read data 2. So what we're going to do is we're going to have another multiplexer to choose between these two values. Do you see how that works? So what's going to happen is we're going to put another multiplexer here. And since it's the source to the ALU, it's known as ALU Source. And so ALU Source is used to differentiate between the read data to input, which is this value here, and the sign extended instruction, which is there, for this input of the second ALU. So it's going to be 0 in the case of an R-type instruction and 1 in the case of an I-type instruction. Does that make sense why we need ALU Source? And so the ALU also receives the 4-bit output from the ALU control. The inputs are the 6-bit function and the 2-bit ALU op control signal. The 32-bit sign extended address is then left shifted by 2 because of what word? Let's see, who else came with? Of course, she disappears. Emily, I get to pick on you again. We shift left 2 by 2 because of? Say it. It's the word right in your tongue. You're about to go. We shift left 2 because of?
Binary?
No.
Binary.
There we go. Very good. I knew you know it. Everyone's going, I'm never going to Dr. Morrison's office hours. He'll pick on me next lecture. No, the thing I was telling Emily is that you know all of this stuff. I'm just trying to convince you that you know it. So me picking on her is my way of indicating to her that I know that she knows it. I know it's in there. All right, so this is your execution stage. What happened is we're getting the values from read data, right? And then read data 1. If you can't see this, let me just zoom in. What this says is ALU Source. I know it's in blue here. And then one value we have is the read data 2 input, right? And then the second value is we have the sign extended value from the mux. So what's happening is we have a choice. It's deciding between an R-type or an I-type instruction. This is ALU source, and here, though you can draw this fine, it's just a 4, and you just do ALU. It says ALU operation. For the TGO, it's acceptable to just draw this in 4 because when we get to the final data path, that's going to be done to the ALU control, right? Which would be. Does that make sense? You see how it's starting to fit together? So what's going to happen here is this value is going to be left shifted by 2 and put into an adder. And this adder here is your PC plus 4. So you get PC plus 4, and this goes into the adder. Now this value is going over here because this is still what happens if we just want to do the next instruction. This value here that comes out of the adder is your PC plus 4 plus your immediate value that's left shifted by 2. What are we calculating here? Y'all just did this on the quiz. What is this value physically calculating? Almost. What type of instruction am I looking for here? Not jump. The other one. Not jump. Branch. You're like, I'm not sure. Why is that branch? Remember how I told you to do it? Let's say we were jumping to 267 and we're at 256, right? And I said minus 1 times 4, right? The reason why is PC is this number. I add 1, so that becomes PC plus 1. When you multiply it by 4, that's your PC plus 4, which is that. 267 is the instruction that we want to get to. What we're actually trying to get to is 267 times 4 because of byte addressing, right? So what we're doing is we know our difference. It's 267 minus 256 minus 1. In that case, it's 8, right? So what's happening here is 8 is the value that's coming in here. 8 is the value that's there. We would want to add 8 if it was an I-type instruction, just for add immediate, right? But what's actually happening is we go here, it's 8. It becomes 32. 32 plus PC plus 4 gives us our branch address, which is actually what we're physically calculating. You see that? That's why you have to do PC 257 minus 256 minus 1. Because this would be the 8 that we're getting out here is the result. Because then we're multiplying it by 4 and then adding it to the program counter. So for an R-type instruction, you're getting 2 values. ALU source is 0. You're putting into the ALU. And then what we're going to see is we're going to eventually put it back into this write data value here. Now this write data value is going to come from somewhere else, so just let it dangle for the time being. Does that make sense so far? All right. Okay, so I want to cover something really quick here that when we were talking about good design requires good compromise. So I find this is a good story of why it's important to understand signed and unsigned, and what we're now done, now that we've actually taken values out of the registers and put them into arithmetic logic unit. This is a good example of why it's good to why am I telling you to actually understand this data path, this advanced digital system, and understand the register transfer language, because goofy things can happen when you don't. And this is a really good example of what happened here. So what happened is back in my day when I was a kid, there's this video game called Civilization. And the whole idea of Civilization is that you picked people throughout history and you try to take over the world with this person, right? Or you try to either create a democracy, you try to become the ruler of the world or the president of the world, however you chose to do it. And it was an 8-bit device. It's specifically MOS Technologies 6502 CPU. And if you recall, you have your two inputs from the ALU. You have your result, your overflow, and your 0-bit, right? And this is the actual chip. So in this particular case, it required 2 cycles to perform add and subtract instructions, but 1 cycle to perform add immediate instructions. Or I'm sorry, unsigned addition. So you know how we have to keep that most significant bit as a signed bit? We did this whole thing in the arithmetic section. So to improve performance, they are trying to actually just use unsigned integers to do this, right? They wanted the game to run faster. But this caused a real interesting problem. So each historical character had an aggressiveness score. And when you formed a democracy, they subtracted 2. So what happened was, you can be Gandhi. And Gandhi's aggressiveness score was 1. And so if you decided to create a democracy with Gandhi, what are they going to do? Subtract 2 with an unsigned integer. So you start out as 0, 0, 0, 0, 0, 0, 0, 1, right? You subtract 2, and what do you get? You get you get this huge number, right? I'm sorry, 1, 0, right? Which is in an unsigned integer 254, right? Which means Gandhi is now the most aggressive person in the game, which leads to things like this. Very well, we will mobilize your armies for war. You will pay for your foolish pride. And greetings from Mahatma Gandhi, ruler and king of the Indians. Our words are backed with nuclear weapons. See, he has conquered Shakespeare and all the other British people, right? So, if you're... the reason I'm teaching you all of these things, and we're going to get into data memory and write back and the full data path next lecture. I think that would be overloading you a little too much, but I'll kind of just use this as an opportunity to see why am I teaching the course this way, this advanced digital system. So you are ultimately going to be having a job where you're either going to be a hardware designer or you're going to be writing some kind of code that works on that hardware. And you have to be cognizant of how the hardware works. In this case, the designers were like, okay, we know that this device runs faster with unsigned integers in addition, right? It takes 1 cycle instead of 2. And so in those instances where your character becomes or starts running a democracy, when it's running at megahertz, it takes 1 less cycle. So in the millions of cycles, you reduce it by 1. Right? They're trying to actually reduce they're trying to improve performance, which is noble. But would you rather reduce 1 cycle when you're running on a megahertz machine, or would you rather try to prevent Mahatma Gandhi from trying to blow up the earth with nuclear weapons? Good design requires good compromise. And this is why understanding the architecture and the organization when writing code is important. And that's why understanding the data path is important. And that's why understanding all the stuff that we did today is important. Right? I'm not just doing this to torture you. I'm trying to, because there's somebody who's out there that's living with this for the rest of their life, right? Like, you coded Civilization. Was that you who made Gandhi a nuclear terrorist? Yeah, that was me. Right? Do you want to be that person? Trying to hopefully help you guys avoid being that person. So by and large, it looks like all of you made pretty strong attempts at the quiz. Well, not everybody. We'll get you there by the exam, right? We have about, does anybody have any questions about this quiz? We'll stop the TGOs at 5.7. 5.1 through 5.7 is the homework. Does anybody have any like a real quick question that? Yes.
Then, since the MIPS doesn't have like a subtraction immediate.
This is a really good question. Yes. Go ahead.
Do you like I was trying to kind of Google it and like go through the textbook, and it said like to use an add immediate and then unsigned or
signed. Yeah, you do choose complement. All right. So he answered his own question. He knows the goofy thing that might come up on an exam. If you look at the MIP screen sheet, you notice how there's no subtraction in immediate instruction? The reason why is because they're trying to reduce the size of the data path. So what they do is they have the compiler-driven encoding of the micro engine. Suddenly all these things I've been saying over and over again starting to come together. That's why section 5 is so fun. The compiler will do a 2's complement of the negative number and then use an add immediate instruction. Does that make sense? All right, on that note, it's 10:45 and you are dismissed. Then he would just be not aggressive at all. He would be 0. Yeah, he would have just been taking a nap, I guess. I don't know. I don't know the whole thing in the game, but it made him the most possible aggressive, which is. Sure. Okay, so you can make office hours by appointment. So you can email me and schedule times. Like if you look at the syllabus, it says the numbers for by appointment. So just if you have a time, and I'm willing to help you out, of course. Homework? Oh, you're not a. Why did I give you this? Is a beer Nasir here? Okay, sorry. Good. Yeah, let's see.
Sir, I read everything to your 4 there, but this deducts 1 point. I don't know why.
You probably, I can see why he deducted the point, because it's drawing.
Oh, the third point.
But it's not worth pointing and all.
Yeah,
I'll give you that flat. Send me an email reminding me to give you a point.
All right. Okay. Thank you.
I see why he took it off, but I can also see why it should be taken off. You know, that's just him being thorough, the thorough TA, and then it's my job to say, all right, now it's like military. He's gunnery sergeant, and I'm the captain.
Hey, I looked at the email you sent out yesterday about the that scholarship opportunity. I was wondering if you'd be willing to help me.
Of course. That's the reason I sent it out.
We can talk about that later.
Yeah, absolutely. Just shoot me. Yeah, you got it.
Thank you.
To jump to the round again. I don't know why not to jump to the.
Your last one's jump.
I mean, this is to jump into the.
Right. Okay, so while is while. Oh, because that first of all, it's kind of you have to jump there. You're saying there should be a jump.
I think if you will be to jump.
Yeah, there should be a jump here. Yeah, there should be. No. Okay, I see what it is. No, if just goes past. While means you're supposed to go back every time. What it's just. Yeah. Yes. No. Yeah, if you just go past it, or while you keep going until this condition is broken. That's why there's a jump. Yeah.
I don't know when to use T0, when to use B1.
Okay.
And find address.
Forgive me. Can you do me a favor? because unfortunately I have a meeting at 11 o'clock, so.